Yep. All right, we're back here. Going to solve now some first order separable differential equations. In the world of differential equations, there's all different types and all levels of complexity. There are courses in college actually devoted to this topic. The great news for you is we are solving the easiest of differential equations that exist. They are called separable, and we're going to stick to first order. So in other words, they're just going to contain a first derivative. All right, so let's just get right after it. So the directions here would say something like this. Find the general solution y equals f of x to the first order separable differential equation, and I'll give you that, right? So find the general solution y equals f of x to the differential equation dy dx equals x over y squared. So that would be the directions here. All right, so how do we do it? Well, we're going to do it by a technique called separation of variables, hence the name separable differential equations. So we're going to take this dy and this dx, and normally we treated this as like the symbol for derivative. All right, so the dy and the dx were really just one thing, one symbol for the derivative. We're going to treat these now as separate entities now. So we're going to treat the dy and the dx as separate entities. So when we go to separate the variables, basically what you want to do is you want to get all of your y's on one side and all of your x's on the other side. And this actually will dictate where you want things. You need your dy's or your dx's or your dg's or your df's or your d whatever. That needs to be in a numerator. It cannot be in a denominator. So in other words, like this dx, we can't have it in the bottom of a fraction right now. So what could you do? Well, if I wanted to, I can multiply both sides by dx here, right? So I can say, hey, I'm going to multiply u by dx and u by dx, right? Multiplying both sides. Here, it's going to cancel, and I'm going to be left with dy equals x over y squared dx, right? Pretty simple. So you're like, all right, so, but I don't want this y squared here because you told me I have to separate the variables. So like right now, all my x terms are on the right side. How do I get rid of divided by y squared? Well, same fashion. I can multiply this side by y squared and that side by y squared. Here it cancels. And now when I rewrite, I'm going to get y squared dy equals x dx, right? Pretty simple stuff there. Now, some of you might be noticing, hey, couldn't I have just cross multiplied this fraction here, right? Dy times y squared is y squared dy, and x times dx is x dx. And the answer is yes, you could have done that. But cross multiplication doesn't always work because it's not always a single fraction equal to a single fraction. And so I kind of wanted you to think about it in terms of what operations could you do to both sides to have this happen. So now when you look at this, you're like, all right, my dy is not in a denominator. My dx is not in a denominator. That is the green light now to go ahead and integrate both sides. So I'll show this as a separate step. So I'm going to integrate y squared dy. So that's integrating the left side, but I'm also going to integrate the right side. All right, and that's just a valid thing that you can do here. Let's make this a large screen. All right, get rid of u and scroll down. So when I go to do this now, it's basically too many integral problems, right? Let me integrate y squared. So that's going to be 1/3 y cubed. And since it's an indefinite integral, it's going to be plus some constant. So I'm going to call that plus q1. I'm just using weird notation for constant, okay? Equals the integral of x, which is going to be 1/2 x squared, plus some other constant, q2, right? And so now what do you do from here? Well, this would be considered an implicit general solution. General because I don't know what these constants are. So I have a family of relations here differing by, in this case, it looks like two constants, such that if I was to take the derivative of that equation, I would get something that would boil down to dy dx equals x over y squared. It would work in that, checking that equation. But I don't want to do that. I want to spruce this. And the direction said solve for y. Now, it didn't say solve for y. It said find the general solution y equals f of x. So this right here tells you solve for y. If it would have said x equals f of y, you would want to do solve for x. So pay attention to that. It's usually solving for y, but they can change that up on you. So I'm going to go ahead and solve for y here. So all right, we know how to do this. This is middle school stuff, and I'll start with the constants, right? So I would get rid of this constant. So I would subtract q1 over here, and I would subtract q1 over here, and I'm going to get 1/3 y cubed equals 1/2 x squared. And then I have one constant minus another constant, but at the end of the day, that's just a constant. So I'm going to do plus c. And now the story with this is I don't really need to show this step. So in other words, let's see here. Can I quickly change my pen color? I can, right? This step right here, I honestly wouldn't even show. I would go straight from here to straight to here. And you're like, well, what do you mean? So in other words, integrate 1/3 y cubed, but don't put the constant in. Even though there is one, don't put it in because you're going to put the constant on the other side, right? And eventually you'd be subtracting this over to get another constant. So just go to here. So go from this step to that step and kind of bypass this. You don't need to do that. Now, you might think, how did you know to put the constant on the side with the x? Well, I'm doing that because it asked me to solve for y. So I put it to the side away from y. If they asked me to solve for x, then I would put it away from x. I would put it on this side. All right. So hopefully that makes sense. If it doesn't, and hit rewind and just keep playing it back until hopefully it does. All right. So here we go. So now we're back to solving for y here. So what would I do? I'd multiply both sides by 3. So I'd get y cubed equals 3/2 x squared plus. Now, technically, I would get 3c, and I could write 3c and there'd be nothing wrong with it, right? But at the end of the day, 3c is just another what? It's another constant. So I'm going to write plus k. Now, certain teachers will just let you write c again, and I don't have an issue with that. I am not going to write c because c is defined here, and really whatever I'm putting here would be 3 times that number. So I change it, and I just keep changing the variable until I run out of variables, which that'll never happen, all right? So what do I do now? Oh, I'm almost close. I don't know if you hear that in the background. That is my dog going bananas on the window right now. There's a good chance she breaks through. We'll find out. Anyway, going back to this. So I want to solve for y. So what do? You're going to cube root both sides, or maybe even better yet, raise both sides to the 1/3 power. So you get 3/2 x squared plus k, and you have to take the entire side and raise it to the 1/3. Not that you necessarily need to show what I'm about to show. Maybe I'll show it just for kicks and giggles, right? If you raise that side to the 1/3, 3 raised to the 1/3 power to power multiply, you just get y to the 1. That's why we did it. And then you can't raise each one individually. Math doesn't work like that. You got to raise the entire side to the 1/3. And this is what you get. So now what is this? And this is real important. This is your general solution. You basically solved for y. So this is your general solution, y equals f of x, all right? Why is it a general solution? Because there's a k in it. We don't know what that constant is. So this is a family of functions differing by a constant k, such that it is going to check in this differential equation. So specifically, the derivative of it would be x over y squared, okay? So that is what you're finding when you find a general solution, a family of functions differing by a constant that satisfies the differential equation. If I wanted to figure out what k was, I would need to give you some information. I would need to give you a point on the graph of y, often referred to as an initial condition. We will do that next lesson. We're not going to do that now. All right, so let's rock and roll, and let's get to the next problem here. All right, so here we go. So let's do another one. I'm going to kind of kick up the juice pretty quickly here. So same directions, all right? Find the general solution, I'm abbreviating, y equals f of x to the differential equation y prime minus 2xy equals 4x. So this is a first order differential equation because it has a first derivative in it. Okay, it's a differential equation because it's an equation with a derivative in it. And we want to find the general solution y equals f of x. In other words, we want to solve for y. So, God, how do I do it? Well, first thing you notice is there's prime notation there. So how do you separate that? Well, you really don't. So your best bet is to change the prime to dy dx. So right away we say dy dx minus 2xy equals 4x. And now, honestly, this is where you should pause the video and you should try and separate these variables. So in other words, following these directions, get all of your y's on one side, get all of your x's on the other side. And remember, this dictates what goes where. So since dy is in the numerator right here, that means your y's have to go to that side. And since dx is in the denominator, that's no good. You need your dy's and your dx's to be in numerators. That means your x is going to go to the other side. So take a second, legit, do this. Pause it and see if you can separate the variables, okay? And see what happens. And you're going to get all sorts of funky things, but go for it. All right? Hopefully you did that. So now, all right, what am I going to do here? Well, I'm going to first actually, believe it or not, add this term over. So I'm going to add the 2xy over to that side. So I add it to both sides and it becomes over here. And that actually kind of seems like counterproductive because you're moving the y away, but you have to initially do that because now your next move would be to factor out, in this case, you pull out an x or a 2x. I'm going to pull out a 2x, and then you're going to get 2 plus y. Right? And the deal is this, right? You really want things connected with multiplication. You don't want things connected with plus, right? If you ever have something like the integral of x and then plus dx, that's no good. And you're like, well, why is that no good? Well, because that's not an integral. That's not the definition of a Riemann integral, right? An integral has got to have the form function, right? Function times dx. And if it doesn't have that form, you ain't doing it, okay? So you want multiplication. You don't want pluses. So you're like, all right, well, how did this help you? Well, because this is what I can do now. I can divide both sides by 2 plus y. So it's going to cancel over here. And on this side, I'm going to get dy over 2 plus y. And at the same time, I'm going to multiply both sides by dx. So here it cancels. And over here, I'm going to get 2x dx. And what's huge about this is, think about it. You have both things connected with multiplication now. This is 2x times x. And you're like, well, this is division. Well, it's the same thing as dy times 1 over 2 plus y. And because it's in that form now, all right, it's going to be what we call Riemann integrable. All right, so I can come over here now and I can say, all right, let me integrate, and I'll even write it this way, 1 over 2 plus y dy, and let me integrate 2x dx, right? So that's me now integrating both sides. So once my variables are separated and my dy and my dx are in numerators and they're connected with multiplication, those are three very important things that have to happen, then I have the green light to go ahead and integrate both sides. So now, all right, let's do the right side first because maybe it's easier. A function whose derivative is 2x, that's just x squared, right? Or you can do 2 times a half x squared. Since I'm solving for y, I'll add my constant of integration to that side. Okay, over here, what would you do over here? Well, to integrate this, back in the day, you do a u sub, right? Because you might not recognize a function whose derivative is this. So you'd say, all right, my Jedi training has told me let u equal the denominator, let u equal 2 plus y, and then go get them. But if you watched Monday's lesson, you would notice that this u is linear, right? So this is a linear u. So when you have a linear u, you can treat this as stuff and do what's kind of like the reverse chain rule. So do you know a function whose derivative is 1 over stuff? And the answer is yes. It's going to be ln absolute value of stuff and then times 1 over the derivative of stuff. So 2 plus y, that's an easy one. That's just 1. So this is kind of a misleading question if you didn't see this, because you might think that you never had to do that 1 over the derivative stuff. But if this would have been 2 plus 3y, you would have multiplied by not 3, but 1 over 3. Okay? So that's what you end up getting here. So now I'll spruce this a little bit. All right, you get the ln of absolute value of 2 plus y equals x squared plus c. So now you have to solve for y. Those are kind of like the directions here. Solve for y. So let's go ahead and make this full screen since we're going long on this one. All right. So if I go full screen here, right, to solve for y, I'm going to exponentiate both sides. This is pre-calc world now. So I'm going to e to that side and I'm going to e to that side. So now the whole idea behind this is e to the ln of something is just the something. These are two functions that undo each other. They're inverse functions. So you're going to get the absolute value of 2 plus y. And over here, you just get e to the x squared plus c. Right? Again, you have to do it to the whole side. It's not e to the x squared plus e to the c. It's this. So now this is where it gets a little bananas, because really calculus ended like right here. Calculus ended here. The rest of this is pre-calc, solving for y here. So now what I'm going to want to do over here is a little rule that you learned in 7th grade, which is when you multiply two terms with the same base, you add the exponents, but you're going to do that in reverse. So you're going to rewrite this as e to the x squared times e to the c. And if you just take a second and see, how'd you do that? Does that make sense? Let's see. If I multiply these two, they have the same base. Oh, yeah, add the exponents. Yep, I would get that. Okay? And the point of this now is because you're getting this times e to the c, at the end of the day, e to the c really can just represent some constant, right? Because e to the c is a number. So I'm going to replace this e to the c with my favorite variable. Maybe I use k now. And I end up getting this. Now on this side, right, I end up having this. And now watch what I do. You're like, what did you do? You just made the absolute value bars go away. Why did I do that? Well, because I have a constant multiplier out in front. And depending on the initial x and y value that you may or may not be given will depend on whether or not this constant has to be positive or negative, because this term is always positive. So long story short, since k has the ability of being positive or negative, I can lose these bars. And now to solve for y, I basically subtract 2 from both sides. My dog is almost through the window right now, if you haven't heard it. And I'm going to get that. And bablam. This is what? What do we have here? This is the general solution. And it's in the form y equals f of x. All right? It's actually called an explicit general solution because we have y explicitly in terms of x. All right. What does that mean in layman's terms? It's basically a family of functions differing by a constant such that it would satisfy this differential equation right here. So if I checked it in that differential equation, it is going to work. And that's it. Okay. All right. So what do we got for homework here? I'm going to give you a couple of questions. I'm going to want you to, let's see, we'll say just basically find the general solution. So same thing, find the general solution y equals f of x for the following differential equations. So the first one will be dy dx equals y over x. The second one will be, actually, is that the same as, nope, it's not. That was x over y squared. Beautiful. The next one will be, we can go bananas here. You want to go bananas? Let's go bananas. Radical 1 plus x squared over 1 plus y times dy dx equals negative x. Good luck with that. And then I'll just give you one more. And so the third one will be, I'm liking this one. This is solid. So dy dx equals 1 plus y squared times x squared. All right, and I'll post solutions to these because you're probably going to need them. Okay, so give those a whirl and let me know how you do. Again, post this in your folder, and we can call this General Soul Chicken. No, I'm kidding. General Soul, and then your last name. Call that the name of the file. All right, when you post it. All right, be good. Stay safe.